Hello friends, welcome back my YouTube channel MS Maths. In this video, I will discuss the code of the finite difference method with the example. Previous video, we have discussed that how the finite difference method, the formula of the finite difference method derived and what is the concept behind this. In this lecture, we'll discuss the example and we'll discuss the example like manually, how can we calculate the finite difference method, and then we will discuss that is for Python code and we will find the numerical solution. It means the approximate solution. And we'll check that our answer is correct or not. So we'll also calculate the error and we will do an error analysis for that so that we can verify that our answer is correct or not. In this video, we'll take a question that solve a BVP boundary value problem, solve a boundary value problem y double dash plus x y dash minus y is equals to f of x. Or I say f of x is nothing but x cos x minus 2 into sin x. This is our equation subject to the conditions boundary values are y0 is equals to 0 and y1 is equals to 0 with the step size 0.25. So the value of x bounded between the x like 0 and 1. So I can say that x is belonging from this interval 0 and 1. Now we'll do the solution for this. So first we have to construct the finite difference scheme for this method for this particular question. So in this case, there is a analytic solution. Okay, so whenever we are going to find the numerical solution to verify that numerical solution is exact, like it stands to exact solution or not, then we should have a analytical solution. So for this analytical solution, so the solution of this differential equation is y is equals to sin x. This is the analytical solution which is satisfied by this equation. This is the non-linear type of equation. In the previous lecture, we have discussed that a linear type of like differential equation and the methodology and the Python code for that particular non-linear differential equation. Okay, first of all, we should convert the ODE into the finite difference scheme. Now, we have the formula of the second order. We will apply the finite difference method for the second order. So the y double dash is nothing but d2y by dx square. It is d2y by dx square. That is basically yi plus 1 minus 2yi. Okay, it means that yi is nothing but I can write in this form that yxi plus 1 minus 2y, because y is a function of x, then yxi plus yxi minus 1 divided by h square. Similarly, we have dy by dx. It is a second order finite difference scheme. Okay, so next this will be f of xi plus 1 minus y of xi plus 1 and y of xi minus 1 divided by 2h. We have these two formula, so we will use these two formula for our numerical scheme, for our finite difference scheme. Okay, now in this case we have to discretize the system. So for that we have to basically we have to divide this interval into the mesh points. So manually, for doing manually, we will do for just n is equals to 3. It means 3 mesh points. So basically we will take for n plus 1. So basically it is n plus 1, that is 3 plus 1 is 4. So the discretization perform in the way that h is equals to 0.25. A is nothing but 0 and B is equals to 1. Okay, A is basically x0 and B is basically xn. I say I want to divide this is into like n is equals to 4 points. Okay, so in this case, if I'm going to divide in this way that I have h is equals to a minus b, or like I can also find the value of n by using the formula that n is equals to n is equals to b minus a divided by h. So basically n is equals to 1 minus 0 divided by 2.5. It is nothing but n is equals to 4. So that if we have n and we can calculate the h. Whenever you have h, then you can calculate the n. Okay, so This n basically represents the number of grid points or number of mesh points. Basically, in the mesh point, there is a like significance of mesh point that higher mesh point gives the more accurate answer for the finite difference scheme. So basically, we'll apply these two formula into this. Before going to that, we should have we should have something discretized point that basically x0 is equals to 0, x1 is nothing but h0 plus h, which is basically 0.25. X2 is basically x0 plus 2h, which is nothing but 0.50. X3 is basically x0 plus 3h, which is basically 0.75. And x4 is equals to, that is xn, or in this way that you can write x0 plus 4h, that is basically 1. So you have x0, 0.2, 0.5, 0.75 and 1. For these points, you have the point that y0 is equals to 0, it is known, and y1 is equals to 0, this is also known. Sorry, not y1, y4. Okay, y4, you have the value of y4, that is basically 0, which is the boundary conditions. We want to calculate y1, y2 and y3. It means we have three unknowns, so we should at least have three equations to find the value of these three unknowns. Then we can find these three values using the system of linear equations. So whenever we are going to putting these two finite difference scheme into our differential equation, so we have differential equation is y double dash minus xy plus xy dash plus y is equals to x cos of x minus 2 sine of x. This is the differential equation we have. Okay, yeah, there is plus and there is minus. So we will put the value and we will find this finite difference scheme. That is basically, I will write x f of xi plus 1 is nothing but yi plus 1. Okay, not sorry, y of xi plus 1 is yi plus 1. I will use this notation instead of this. So it is yi plus 1 minus 2 yi plus yi minus 1 divided by h square plus xi. I will write it like in the discretized point. I will write x instant. I will write xi instead of x, and this is basically yi plus 1 and yi minus 1 divided by 2h. This is the discretized formula, the finite difference formula for the y dash. Minus yi is equals to xi cos of xi. Oh, instead of writing this, I will write just f of. So I will write f of x1. So I will consider that f of x is equals to x cos of x minus 2 sine of x. Now, I'm going to separate all these values, then I will find that 1 upon h square minus xi upon 2h into yi minus 1. That will be the lower diagonal for the tridiagonal system of matrix, plus minus of 2 upon h square minus 1, that is yi. The coefficient of yi and coefficient of yi minus 1 we have written that 1 upon h square plus xi upon 2h yi plus 1 is equals to f of xi. Now we have this generalized system of equation and this recurrence relation. This is basically three-term recurrence relation that we have yi minus 1, yi and yi plus 1. Now, where I is running from, because of that, we want to calculate the values for these three, 1, 2 and 3. So I will running from 1 to 3. Okay, 1 to 3. Because of that, I always running from 1 to n minus 1. Because of that, 0th value we know, nth value we know by the boundary condition. We should, like, we want to calculate the values at 1, 2 and 3. For these values, so we'll put this I and we'll get a system. Now, in this case, just for simplification, I will consider the AI. It is nothing but AI. It is BI and it is as CI. Okay. So now, if I will put the I is equals to 1, so that will be A1 Y0. plus b1 y1 plus c1 y2 because of I plus 2, and it will be f of x1. Okay, f of x1, that the function of value at that x1 point, and x1 is nothing but 0.25, which we have already calculated in this table. Now, here we know that y0 is equals to 0. So basically a1 y0. So it is 0, or this is constant basically. So we'll write b1 y1 plus c1 y2 is equals to f of x1 minus a1 y0. Because of that, this value is 0 due to the subjective conditions that f of x1 minus this term will goes to 0. So this will be basically f of x1. So it is our equation number 1. Now we will put the x equals to 2, then we'll get, I is equals to 2, then we'll get a2 y1, because 2 minus 1 1, plus b2 y2 yi, plus c2 and y3, that is equals to f of x2. We know that in this particular equation there is no constant term. It means there is no known term. So it is itself equation number 2. There is no modification in this equation. Now, similarly, we'll proceed to the I is equals to 3. That is nothing but I is equals to n minus 1. So in this case, we have a3, I minus 1 is y2, plus b3 is y1, y3, plus c3 is y4, and we know that y4 is again known. So that in this case, we will modify this equation as y3 y2 plus b3 y3 is equals to f of x1 minus c3 y4, and we know that y at xn, that is x4, is equals to 1. The boundary condition y0 is equals, y1 is equals to, in this case y1 is equals to 0. Okay, so basically there is the value that c3 is nothing but that in this case the boundary condition is 0. We have y1 is equals to, okay, let me check this boundary condition. Y1 is equals to 0. So for this there will be a change. Wait, y1 is equals to 1, then change this with y1 is equals to 1. Then this is we will take it as the exact solution. Okay, so we'll compare with this solution. Now we have that y1 is equals to 1, then we will put y4 is equals to 1. So basically it is a3 y2 plus b3 y3 is equals to f of x1 minus c3. Now we have all these values, then how can we find a1, a2, a3? Obviously we will put x1, x2, x3, and for this value that we can calculate the value of this. Now manually we have calculated all the things, then we got that value. I want to write all the value, that a1 is equals to 15.5, a2 is equals to 15, a3 is equals to 14.5. By putting this value within the formula, ai is equals to basically 1 upon h square minus xi upon 2h, and bi is basically minus 2 upon h square minus 1, and ci is 1 upon h square plus xi upon 2h. Similarly, that is b1 is equals to minus 33, b2 is also minus 33. Because of that, all the values will be equal because it is independent from x. So it is obviously 3 minus 33. So c1 is equals to 16.5, c2 is equals to 17, c3 is equals to 17.5. Now by using this, we will we will construct the finite system of equations. Okay, so we will have b2 c3 0, the matrix, coefficient matrix, this, and a2, because of that you can see here a2, b2 and c2. So a2, b2 and c2, this will be 0 because of there here is a3 and b3. It is tridiagonal system. You can see this is the tridiagonal system of equations, system matrix. Then we want to calculate the y1, y2 and y3 only. So the right hand side, that will be, we have calculated all the right hand side. So we have got that 0.2526 minus 0.5200 and minus 18.3145. All these value we have calculated with the help of calculator. Now, by solving this equation, we got that y1 is equals to 0.2868, y2 is equals to 0.5584, and y3 is equals to 0.80034. So y0 is equals to 0 and y1 is equals to 1. So these all the value that we have compared with the our solution, and like by solving this equation, so we got this in like answers. Now this complete method will perform with the Python code. Like all these steps clear that first we will discretize the system, we have the values, and then go for the basically the solution, and we will solve this matrix using the sparse matrix. Sparse matrix is one of the matrix in which that will like that matrix will store that type of matrix or that type of particular library will store only non-zero values, that neglect the zero values, or they will not like store the zero values in the our system. Okay, so basically we will find the solution using the sparse matrix. That like the importance or significance of the sparse matrix, that we can find the solution with the less computational cost. Okay, now in this case we will discuss the Python code. Okay. So this is our ordinary differential equation, which we have which for which we want to calculate the value. So it is for 1 and y0 is equals to 0. Now in this case we have imported some library like numpy, scipy, is like scipy dot sparse for diagonal, like to making the tridiagonal system and solving the system. And we have like a0 is equals to 0, b is equals to 1, and this is for n is equals to 4. Then it will calculate the h value, that will be 0.25. Okay, I want it is the just the solution for this. You can see it is the value of the h, and it is the x, that discretized the value of the x, that 0.24 like 0.25, 0.5, 0.75, and 1. And we have like discretized this system as in like using this np dot linear space with the a to b with the n plus 1 numbers. Okay, so we have printed all these numbers. Then now in this case we have linear like li, which is the lower diagonal. We have like assigned the zero array with the help of numpy, that np dot zeros n minus 2. Because of that we have n is equals to 4. Okay, we have n is equals to 4, then up to n minus 2. Now the li, it is the lower diagonal. Lower diagonal is 0 with the range of n minus 2. Because of that, in this case you can see here, wait, in this case you can see here we will start the AI values with the A2 and A3. So we need only A2 and A3 values. It means we have n is equals to 4. We need only two values. So the range for this particular array is n minus 2. And similarly, the range of this particular array is also n minus 2. So you can see here, this is n minus 2 and upper diagonal is n minus 2, but the lower diagonal is n minus 3. We need the three values for this array. Similarly, okay, we have doubly assigned this value. Okay, wait. Okay. Now in this case, you can see here that we have put the formula of the lower diagonal. Lower diagonal is the basically coefficient of yi minus 1. Okay, this is the lower diagonal. So this we have assigned the value that you can see 1 upon h square into xi upon 2 into h. Okay, so this is basically that ranging from 0 to n. Okay, I starts from 0, that we can put that I minus 2, that if I is 2, then it will start from 0, because in Python array that will be indexing starting from 0. Similarly, similar manner, we have started this for 1 to n. Because of that, in this case, we need 1 to n. It means 1, 2 and 3. Okay, n is 4, that obviously the for loop will consider the n minus 1 values. So we need 1, 2, 3 values. So in this case, we have put this value that basically 1 upon yeah, it is I think minus 2 upon h square minus 1. So I think there is a mistake. Okay, this is upper triangle. Sorry, upper diagonal. Sorry, this is upper triangle. So it will start from 1 to n. Okay, yeah, this is the diagonal system that we will we have we have wrote here, that I we have written here that I is in range 0 to n minus 1. Okay, 0, 1, 2. It means that starting in the our language, that 1, 2, n minus 1 is 3. So it goes to 1, sorry, 0, 1 and 2. So all three's value in the diagonal. Like this is the formatting, this is the way that how to make the discrete how to make the tridiagonal system. So now using this lower triangle, lower diagonal, diagonal and upper diagonal by this particular syntax, this is the sparse syntax that we have made this particular tridiagonal system, that you can see minus 33, minus 33 for 16.5, 17, 15 and 14.5, that we have already written here, that you can write all these value. We will not use this value and this value. Okay, because of that, okay, wait, we will use only B2, not C3, it is C2, C2 and it is C3. Okay, I think I made a mistake with this. B2, C2 and not B2, C3. I should start this with B1. Okay, I think I made a mistake here, that B1, C1, A2, B2, C2. Okay, yeah, this is the correct. This is the correct scenario. Okay, now this is the correct system, that yeah, it is. You should correct this value now. So this is for the particular syntax to printing this tridiagonal system, that we can put all these value and the solving the linear system. Yeah, there is the gamma is basically that right hand side. In the right hand side, the boundary condition, because of that first boundary condition is basically 0. In this case, you can see here, this is nothing but f of x only. So we have we didn't change this value ever. Because of that, there is no non-zero value. So we have changed the last values, n minus 2, the last index with this. You can see here all the system, all these values are same, but we have subtract this yi n minus 2. Because of that, this is yi n minus 2. What is yi n minus 2 is nothing but C3. Ui n minus 3. No, I'm just saying that ui, that ui n minus 2. Ui n minus 2 is nothing but ui is the upper diagonal. Upper diagonal means this is u0, this is u1 and this is u2. u2 is nothing but ui n minus 2. n is 4, then you can see it is 2. So it is upper diagonal. The last value of the upper triangle we will subtract within this. So after that, we will solve the system, that np.linearalgebra.solve that a and gamma will solve this and we will get the result. And we have the exact solution for this is basically sine xi. Okay, so this is the exact solution. We have considered that this is not like proper exact solution. We have just considered that this is the exact solution, and we'll compare this and we'll plot, we'll find the error, the absolute value of the result minus exact solution, and we'll plot this. Now you can see here, this is the error. Yeah, obviously there is a slight error between this, that you will see that this is the particular graph for this. If I will increase the mesh points, then it will like slight more accurate. I will take 100 mesh points, so it will be basically slight like in this way. Wait. Okay, I think there is a mistake. It shows the mistake within the I. I made a mistake with this. Wait, just. This is the this is the answer. I don't think so. There should be a mistake. I minus 1, then it is n. I think it should be n minus 1. No, it is n ranging from 1 to I minus 1. That if I will then use 0. If n is equals to 2, then it will be 1. 3, then it will be 3xi3. Yeah, it is correct. I think there is an issue. I don't know, but yeah, this is the correct answer. Okay, this is the correct answer for this. If you will run the code, then this is the proper correct answer that we have already run in this video. I don't know why the error it is showing in this. I'll check it. Okay, so this is the proper code that we have discussed within the lecture. I hope you got the complete concept of the finite difference method, that how to solve the equation. We have solved two problems on this. So thank you. Bye bye.